Hi students, this is the spiral review for Spiral 5. That's the spiral that you will have tomorrow. First off, we're going to talk about domain and range. It's one of our two graded sections this time. And in terms of domain and range for this graph, we know that domain is going to be based on x values. So we need a starting x point and an ending x point. So I'm going to call this the low and high. And looking at this, we've got a lowest x value of -2 and a highest x value of 4. So that's my domain. Similarly, for range, we need a lowest y and a highest y. So if I take a look, my lowest y value is -1. My highest y value is +2. My range is going to be -1 to +2. For the next part, identify an interval on j of x that is both negative but increasing. So those are the two things I need to be aware of. In terms of this, first thing I want to talk about is negative. Negative means below the x-axis. So any point that's down here falls into the negative category. The second thing is I need points that are increasing. That means that we're going up from the left to right. So this would be increasing. This would also be increasing. But everywhere else on this graph is decreasing. The only place on this graph that is both negative and increasing is this part right at the end here. And I'm going to circle that. In terms of x values, because we use x values for our intervals, this starts at 3 and it ends at 4. Looking at number 4, local maximum and local minimum on the graph, let's talk about maximum points first. We have a maximum value up here. You could also consider this a local maximum at the end. Either one of those could be considered a max. In terms of local minimum, that is a local minimum down the bottom. And this could be a local minimum as well. Those are the points that are the highest or lowest around their respective values. For number 2, this is the first time that we're graded things. I don't know why I called this number 2. But we're combining functions. Second section is what we're looking for. There we go. Okay, we've got a couple different functions written in algebra. One involves a square root, and one involves a line. We've got a table that's m. We've got a graph that's j. It happens to be the same graph we had in the previous slide. Okay, L plus k of 4 means we're looking for L of 4 plus k of 4. Those are my two equations up above. So the first thing I might do would be to do L of 4. I'll do this up here just so I have some room. L of 4 is going to be 2 plus the square root of 4. Square root of 4 is 2. 2 plus 2 is 4. K of 4 is going to be 4 times 4 minus 7. 4 times 4 is 16. Minus 7 is 9. 4 plus 9 is 13. Second one, 2m of 5 plus 3j of 3. First I've got to find m of 5. And m is the table. I find 5. I've got an output of 8. J of 3. That's going to be my graph. So I'm going to find where x is 3. And I've got a height of -1. So we've got to do 2 times m of 5, which was 8, and then plus 3 times j of 3, which was negative 1. 16 minus 3 is going to be 13. 2 13s in a row, that's weird. Okay, number 12. We've got to find 2m inverse of 8 and 2m inverse of 2m of 8. Oof! That's complicated if we got both of these things going on. M inverse of 8 is asking us to go backwards. So we're looking where we have a y value of 8 and putting the input in there. That's going to be 5. And then m of 8 is asking us to look for where the input is 8 and give us the output. Inverses and non-inverses ask us to kind of go back and forth between inputs and outputs. Okay, so 2m inverse of 8 means 2 times 5, minus 2m of 8 means 2 times 3. 10 minus 6 is going to be 4. Alright, the last part of this are some inverses. I decided to put a few examples in the video this week because I know that's something you've been struggling with. I'm going to do each of these kind of separately here. So k inverse of x, we're going to start with y equals 4x minus 7. I'm going to switch my x and y. That's always the first step of the inverse, 4y minus 7. I'm going to add 7 to both sides, so we get x plus 7 is equal to 4y. And finally, divide both sides by 4, and I get a value of y is equal to x plus 7 over 4. For m inverse of x, that's the table. I'm going to move that a little bit. So we're looking, I'm going to erase the third line so I have some more room here. So we need x and m inverse of x as our table values. And all we're doing is switching our x and our y's. So where we used to have 8, 3, now we have 3, 8. Where we used to have 6, 0, now we've got 0, 6. And where we used to have 7, 9, now we've got 9, 7. And where we used to have 5, 8, now we've got 8, 5. That's how you do an inverse for a table. And finally, we've got L of x we got to take the inverse of. So that's going to start out as y equals 2 plus the square root of x. I'm going to switch my x and y. X equals 2 plus the square root of y. I'm going to minus 2 to both sides. X minus 2 is equal to the square root of y. And then I'm just going to surround the x minus 2 in parentheses, because to get rid of a square root, we've got to square both sides. And I'm just going to leave this as is. You don't have to do anything else besides this. For our third section, this is going to be on transformations, and this part is just feedback this week. The video I'm going to do is for the bottom parts of this. So we've got the solid line transformed to become a graph of the dashed line. So we want to go from f to g of x. I really recommend that you always start with the words of what's going on here. These look like the same shape, just kind of moved around. I'm just going to check an endpoint because those are pretty easy for us to see. And this looks like it's going something like that. So 3 left and 4 up. Just to make sure, I'll check the other endpoint. 3 and 4. Nice. And if I check that kind of middle point, 3 and 4. So all three of these are the same. That's just me being a little bit careful with this. So I know I need this to be 3 left. That would mean in parentheses I'm going to have x plus 3. We know this is going to be an f of x function. And then for 4 up, that's going to be plus 4 at the end. At this point, you're done. For h of x is equal to f of negative x plus 3. This is one of the ones that we're probably not going to end up doing on a spiral type thing, because negative x means a horizontal flip, and generally I'm going to avoid those. Plus 3 means up 3. So the way that I'm going to do this, I'm actually going to move this up 3 first, and I'll do this in, I guess, in a highlighter, just so it's a little bit lighter. So my original graph, it's going to go up 3, and it's going to go up 3, and something like this. Okay, now I'm going to do the last part, which is the sketching this in blue. So horizontal flip means each x coordinate is going to be flipped onto the other side of the y-axis. So this point would move to here. This point would move to here, so that would be the linear part of this graph. And the point that's at 5 now would move to negative 5. And that's going to be the curvy part of our graph. So something like that where it's been moved up and then flipped horizontally. Next we have the new section. This is graphing and solving. This is also feedback only. On here it's 2 pages. It's not going to be 2 pages on the actual spiral. I just want to give you lots of examples and lots of room to write stuff. For number 19, we've got to write an equation for the dashed line. That's this guy right here. I gave you the mother function for the parabola if you want it. You don't have to use it if you don't. I'd like you to notice that the vertex is at 3, 2. In other words, this has been moved over 3 and up 2. It's also been flipped vertically, but the points on either side of the vertex are still only 1 and 1, just like in our original. So what I might do for this is write something like n of x, because that's what we're dealing with. I know for my vertex it's going to be x minus 3 squared plus 2. And then I know, since this is upside down but not changing the shape, it's just going to be minus 1 in front. For number 20, first thing I notice is that this is an absolute value function. It's going to be a v. I know that the vertex is going to be at 1, 2. Skipped a page. And that the plus 2 in front means that we're going to go up 2 over 1 on each side. Basically, that's it. That's what you need to do in terms of graphing this thing. This is a really quick problem if you know what you're doing. 21, we got to solve an absolute value algebraically. By algebraically, what I mean is I really want to see, even though this is a pretty straightforward one, x plus 1 equals 3, and negative x plus 1 equals 3. So if I minus 1 to both sides, we get x equals 2, and we end up with negative x minus 1 after we do some distribution of that negative. If I add 1 to both sides, divide by a negative, we end up with x equals negative 4. All right. Looking at the graph, what this is really asking you to do is to say, how does this graph connect to the problem you just solved? And what we're talking about is these are the intersections. So the x values of the intersections tell you the same thing that we just did in terms of solving. Just a way to solve graphically. Okay. We've got a piecewise function. We've got to find v of negative 3. That's the video part of this. So for v of negative 3, I'm going to check both of these. Negative 3 is not less than negative 3. Not going to use that one. Negative 3 is definitely equal or greater than negative 3. I'm going to use my second stem here. So what that means is that I'm just going to plug negative 3 into that part of the equation. So negative 3 plus 3, which is 0. And for v of 11, again, I'm going to check both stems, even though I can pretty clearly see where this is going. 11 is not less than negative 3. 11 is greater than or equal to negative 3. So I'm going to use this stem again. And 11 plus 3 is going to be 14. The last page is all about what we did in class yesterday, which is really about understanding and interpreting functions. We've got an equation going on up here. This is not useful for us in terms of vertex form, but that's okay because I give you a graph and you've got all kinds of points going on here. Ooh, there we go. Question 23, which is a video question. How high off the ground was Mr. Butterworth when he threw the ball? So to me that sounds like a beginning of the problem. That's going to be a y-intercept question. In terms of our graph, the y-intercept is going to be 0, 6. I'm going to say he is 6 meters off the ground. The equation that we're given in this problem, negative 5t squared plus 5t plus 6. We know that a y-intercept happens when x, or I guess in this case t, is 0. So if I do t equals 0 in here, we get 0 plus 0 plus 6, which gives us the same thing. Y-intercepts can be found both graphically and algebraically pretty quickly. When will the ball hit the ground? As soon as I see hit the ground, I want to think about this as the x-intercept. So in this case, I've got two different options, but one of them's got a negative time because the x-axis or t-axis here is time. So at 1.704 seconds, that's my positive x-intercept. It's going to hit the ground. And for the graph, we're looking for x-intercepts. Okay, number 26. How high will the ball be after 1 second? What this is asking us to do is to plug in 1 into this equation. So negative 5 times 1 squared plus 5 times 1 plus 6. So that'd be negative 5 plus 5, and that's going to be equal to 6. So after 1 second, it would be 6 meters off the ground. That's kind of weird, same as it was when it was let go. Oh, and I guess that makes sense based on my graph, because that's where 1 is, and that's the same height. Weird. The second one is where the weird calculation is going to come in. So we're going to have negative 5 times 2 squared plus 5 times 2 plus 6. 2 squared is 4, times negative 5 is negative 20, plus 10 plus 6, that'd be negative 4. And that'd be like 4 meters below ground, which doesn't really make sense. We mentioned that if you look at these problems and you get numbers that don't make sense, it might just be because the math only works for a certain part of this problem, like when it's in the air and just about to hit the ground, not when it goes underground, because balls generally do not go underground when you throw them.